If humanity were to suddenly vanish tomorrow, the Earth wouldn't forget us by the next morning. It would keep spinning, clouds would continue to drift over cities, and tides would keep surging into harbors. But from that moment on, a cleanup operation longer than any empire would begin. 10 years later, the power grid would fall silent. A century later, many cities would begin to crumble. Thousands of years later, the vast majority of texts, screens, photographs, and names would vanish. But in Earth's deepest memory, some things will not fade so quickly. They will seep into the ocean floor's silt, ice sheets, trees, coral, soil, and rock, becoming a signal that future geologists will recognize at a glance. Here once lived a species that briefly burned the carbon beneath the ground, reshaped global life, and scattered materials across the planet that had never existed in nature. The real question isn't which building will be the last to fall. The real question is this: hundreds of thousands or millions of years from now, when no human language can be deciphered, when continents have shifted and coastlines have changed, what evidence will Earth retain of us? The skeleton of a city, a piece of plastic, a layer of radioactive dust, or the void left by a mass extinction? Tonight, we'll journey forward through time, from the very first day after humanity's departure, all the way to the distant future when the sun ultimately reshapes Earth's fate. If you're ready to see just how fragile civilization is in the grand scale of time and how deep a mark it can leave, don't forget to like and subscribe. Get ready. Let's begin. First, let's clarify one thing. Earth doesn't remember anything, at least not the way humans do. It has no archives, no memories, and it won't miss a city or a song. Earth's memory is physical and chemical. It compresses events into sedimentary layers, inscribes death into fossils, records atmospheric changes in ice cores and isotopes, and buries the debris left by floods, volcanoes, and impacts within rocks. We know that an asteroid struck Earth 66 million years ago, not because Earth told us the story, but because there is an unusually high concentration of iridium in rock layers all over the world. That thin boundary layer is the testimony left behind by deep time. Therefore, to understand what humanity will leave behind, we cannot look solely at the things we consider great today. Skyscrapers, data centers, bridges, museums, and satellites are incredibly sturdy on a human scale. But geological time does not respect the human scale. A glass curtain wall faces diurnal temperature fluctuations, wind, salt spray, plant roots, and gravity. A steel bridge faces oxygen and water. A server faces moisture, corrosion, and microorganisms after a power outage. Once maintenance ceases, the most complex parts of civilization are often the first to fail. The Earth won't destroy them first. It will simply stop letting us shield them from natural processes. Suppose humanity were to vanish simultaneously, not leaving behind any distinctive traces of destruction caused by war, plague, or an impact, but in a nearly silent manner. In the first few hours, cities would appear almost unchanged. Traffic lights might still be lit, power plants might continue to run on autopilot, airplanes would run out of fuel or be guided by automated systems if no one took control, subways would come to a halt in the tunnels, and the last messages would still be flashing on screens. But modern civilization is not a collection of independent machines. It is a network that requires constant error correction. Fuel must be replenished, valves inspected, dams maintained, power grids balanced, and fires extinguished. Without humans, the system would not explode all at once as it does in the movies, but would lose stability at different locations and at varying speeds. Within days to weeks, the most noticeable changes would occur in electricity and water supply. Many power generation facilities would shut down due to fuel shortages, cooling issues, scheduling problems, or safety protocols. While conditions vary by facility type and region, one conclusion is certain. Without maintenance, a widespread and stable power supply cannot be sustained for long. Once pumping stations stop operating, water tanks in high-rise buildings would run dry, underground spaces would begin to flood, and sewage systems would lose power. The city would go dark block by block at night, not swallowed up by some massive catastrophe, but rather like a circuit board that has lost power, with the lights fading one by one from the periphery toward the center. A year after humans have left, in many places it is not large animals, but plants that are the first to regain vitality. Seeds are already present in cracks. The wind brings new ones, and birds and small mammals carry seeds into streets, parking lots, and rooftops. Without pruning, weeding, drainage, or pavement maintenance, water would pool in the lowest spots, and roots would burrow beneath the asphalt. Asphalt is not an eternal black rock. It ages and cracks under the influence of ultraviolet rays, thermal cycles, and shifting loads. A tiny seed is not powerful, but it doesn't need to defeat an entire city. It only needs to wait for a crack. This is a force that is easily underestimated. When humans build roads, they first clear away surface vegetation and soil, then lay down gravel, asphalt, and concrete, as if to permanently set the ground in place. But the Earth's surface is never static. Rain washes away fine particles, frozen water expands within cracks, and groundwater alters the underlying strata in unseen ways. Roots are not bulldozers, yet they can exploit existing weaknesses to steadily expand their hold. Decades later, an unmaintained highway may still be recognizable as a road, but it is no longer a road. It has become a man-made terrain covered by shrubs, standing water, and a crumbling surface. The fate of buildings is no different. Wood is gradually broken down by fungi, insects, and moisture. Steel rusts under the combined effects of oxygen and water, and the volumetrically expanding corrosion products in turn cause concrete to crack from within. Concrete, though durable, is slowly altered by water, carbon dioxide, salts, and repeated freeze-thaw cycles. There is no single universal urban lifespan. Stone and concrete in arid regions may last longer, while vegetation and erosion will take over more quickly in humid tropical areas. Coastal cities must also contend with salt fog, storm surges, and sea level changes. The truly reliable statement is not that all cities will disappear in a certain year, but rather that once maintenance ceases, cities will quickly revert from precise machines to piles of constantly weathering materials. Perhaps the first thing to become unfamiliar in a city is its sounds. Without engines, air conditioning, crowds, or the constant low-frequency vibrations of traffic, many areas would once again hear the wind, water, insects, and birds. Soon after, animals would move along the corridors left behind by humans. Railroads, river embankments, power transmission corridors, and suburban greenbelts might temporarily become new migration routes. Fences will collapse, and farmland will gradually evolve into grasslands, shrublands, or forests. The specific outcome depending on climate, soil, fire, and the original ecosystem. Not every place will immediately revert to pristine nature. Many species have already been introduced by humans to new continents, and many ecological relationships have been altered. after humans disappear, the Earth will not return to the past. It will simply enter a new future without humans. The oceans, meanwhile, will take over the coastlines more slowly and more ruthlessly. Ports, subway entrances, underground parking garages, and low-lying neighborhoods, which once relied on pumping stations, floodgates, and levees to stay dry, will be vulnerable. Once the levees fall into disrepair, torrential rains, storm surges, and seawater erosion will find their way in through the weakest points. Coastal cities will not sink neatly beneath the water. They will first be flooded in localized areas, with breaches expanding through repeated episodes of extreme weather. Salt water will seep into the concrete and rebar, accelerating corrosion. Sediment will cover the ground, and the tides will begin to mark their own rhythms on what were once streets. In future geological strata, a port city may no longer be a distinct grid of city blocks, but rather a chaotic deposit of bricks, glass, plastic, metal, seashells, and silt. Many would speculate that the pyramids, the Great Wall, or skyscrapers will become humanity's final monuments. While they may indeed outlast paper and electronic devices, lasting a long time is not the same as lasting until the very end. Stone weathers, earthquakes, bring structures crashing down, groundwater and salt seep into cracks, and ice ages and floods carry away fragments. Even if certain large-scale ruins remain recognizable thousands of years from now, they will mostly be concentrated in a few regions. The Earth's deep memory favors widespread, simultaneous signals that can be buried, rather than magnificent structures standing alone in a single location. The fate of paper and digital records is even more unpredictable. Paper books in libraries may survive for a long time in a suitable dry, low-oxygen environment, but most paper is destroyed by water, mold, fire, insects, and acidic materials. Digital information may seem intangible, but it actually relies on an extremely fragile layer of physical components: electricity, servers, storage media, reading devices, software, encryption, and language. Hard drives fail, flash memory degrades, magnetic tapes lose their magnetic properties, and optical discs are subject to material aging. Even if the outer shell of a data center still exists centuries from now, the information inside will likely have long since turned into unreadable noise. Humanity's richest memories may be the most short-lived layer of our legacy. But some underground spaces prove more resilient. Tunnels, mines, subways, and underground warehouses are partially shielded from the elements and ultraviolet radiation. They may preserve the outlines of human activity for a very long time. Regular cavities, support structures, metal debris, layers of waste, and anomalous concrete and backfill materials. Yet even the underground is not a secure vault. Groundwater seeps in, rock strata deform, ceilings collapse, and microorganisms alter the chemical environment. Hundreds of thousands of years from now, many underground structures will no longer be hollow monuments, but will be filled with debris, water, and new sediments, becoming an unnatural disturbance in the geological record. At that point, one of the most dramatic relics might be nuclear facilities, though this must be described with caution. Reactor designs, fuel states, and safety systems vary from country to country. They cannot all be portrayed as doomsday devices destined to explode. Once maintenance ceases, some facilities will face serious risks related to cooling, power supply, and material degradation, and localized contamination may occur. Meanwhile, specially designed deep geological repositories aim to isolate high-level radioactive waste using stable rock formations, multiple barriers, and extremely long time scales. Whether they can remain completely intact under every conceivable geological change in the future is a matter of ongoing engineering and geological assessment, not something that can be answered with a simple declaration of eternal safety. Even so, the most globalized mark left by the nuclear age may not come from a single reactor, but rather from the atmospheric nuclear tests of the mid-20th century. Radionuclides produced by nuclear explosions spread through atmospheric circulation and settled into lakes, oceans, glaciers, and soil. In many undisturbed sedimentary layers, the appearance and peak levels of plutonium isotopes help researchers identify sedimentary strata from the 1950s and 1960s. Unlike a building, it is not conspicuous, yet it is almost like a timestamp imprinted on the Earth's surface. Future researchers will not need to know our language. Simply by measuring the isotopic ratios in that layer of sediment, they will know that a civilization capable of splitting atoms once existed here. The half-life of plutonium-239 is approximately 24,000 years. This means that after 24,000 years, it will not have completely disappeared. Rather, about half of it will have decayed into other nuclides. After another 24,000 years, the remaining half will be reduced by half again. This figure is easily misinterpreted to mean it will exist forever. In reality, radioactive decay and geological preservation are two distinct phenomena. Even if an isotope has a very long half-life, it can only serve as a readable signal for future generations if the sedimentary layer remains free from erosion, mixing, transport, or burial to depths where it becomes unrecognizable. But compared to a single city, global nuclear test fallout has a terrifying advantage. It is not a single-point relic, but rather a widespread, contemporaneous chemical imprint. If radionuclides are like a timestamp, then plastic is more like a material invasion. Plastic is not a single substance, but a broad class of man-made polymers. Under the influence of sunlight, oxidation, friction, and microorganisms, they degrade, become brittle, and break down into increasingly smaller fragments. This does not mean they disappear quickly. Many plastics simply transform from visible bottles, bags, and fibers into harder-to-track microplastics and nanoscale particles. They are carried away by the wind, transported by rivers into the ocean, ingested by animals, and then moved to new locations via feces, sedimentation, and the food chain. Whether plastic will persist in its original polymer form millions of years from now depends on where it is buried, whether it is exposed to oxygen and light, the temperature and pressure conditions, and whether it is subsequently melted or degraded. No scientist can honestly claim that every piece of plastic will survive until a specific year. But geology is not concerned solely with a single intact plastic bottle. Large quantities of plastic debris have already entered coastal areas, estuaries, lakes, and deep-sea sedimentary environments. Some have even combined with rocks, sand grains, and organic matter to form new mixtures. Even if the polymers themselves gradually change, their unusual forms, accompanying additives and sedimentary contexts, may still become part of the geological fingerprint of the Anthropocene. Even more peculiar is the possibility that future rocks may contain combinations of materials that are not naturally occurring minerals. Metallic aluminum rarely exists in its pure form on the Earth's surface because it readily reacts with oxygen. Yet humans extract it from ore on a massive scale using high temperatures and electricity. alloys, glass, concrete, refined metals, synthetic fibers, electronic components, and ceramics will enter landfills, urban sediments, and the seabed in quantities far exceeding those found in natural settings. Geologists refer to these man-made or heavily human-influenced materials as technofossils. They are not fossils like dinosaur bones, but they may become some of the strangest fragments in future rock layers. Concrete, in particular, deserves a closer look. Though seemingly ordinary, it is the largest man-made rock in modern cities. The total volume of concrete produced by humans is immense, and bridges, floor slabs, dams, roads, and underground structures all rely on it for support. In the future, it will crack, crumble, and be transported by water and sediment. Some fragments will enter rivers and beaches like natural gravel. Others will be covered by new sediments in landfills and urban ruins, gradually cementing together. In rock layers millions of years from now, it may not be possible to recognize a specific building, but a layer of urban conglomerate, containing an unusually high concentration of concrete fragments, glass, bricks, and metal oxides, may emerge. However, materials are not humanity's largest-scale legacy. The real turning point lies in the air. Coal, oil, and natural gas, formed hundreds of millions of years ago, buried underground the carbon that ancient organisms had sequestered through photosynthesis. In just a few generations, humans have rapidly extracted and burned a portion of these resources, effectively unlocking a carbon reservoir that had been sealed away by geological time. Once carbon dioxide enters the atmosphere, it does not dissipate like smoke within a few days. Instead, it is redistributed among the atmosphere, terrestrial ecosystems, the surface ocean, the deep ocean, and rocks. A process that spans timescales ranging from years to tens of thousands of years or even longer. The Intergovernmental Panel on Climate Change, IPCC, notes that a portion of emitted carbon dioxide will remain in the atmosphere for hundreds to thousands of years, while its redistribution back into geological reservoirs will take tens of thousands to hundreds of thousands of years, or even longer. The exact proportion depends on total emissions, future land use, ocean absorption, and Earth system feedbacks. Therefore, this cannot be reduced to a simple countdown. But the direction is clear. Even if humanity stops emitting carbon dioxide, the climate system will not return to its pre-industrial state overnight. The ocean's heat absorption, the response of ice sheets, sea level rise, and the carbon cycle all have their own inertia. The mark we have left in the atmosphere will be erased by the Earth at an extremely slow pace. Deeper evidence comes from carbon isotopes. Fossil fuels originate from ancient organisms, and organisms tend to select lighter carbon isotopes during photosynthesis. The massive burning of fossil fuels causes a measurable shift in the carbon isotope composition of the atmosphere, oceans, and some sediments. This shift is not a signature unique to humans, as volcanic activity, oceanic changes, and ancient disturbances in the carbon cycle can also produce similar phenomena. The truly compelling evidence comes from the combination: rapid isotopic changes, rising greenhouse gases, soot particles, heavy metals, plastics, radionuclides, and shifts in biotic communities, all appearing together in adjacent geological layers. The Earth's memory rarely relies on a single word, but rather on the entire sentence. The ocean preserves a large part of this sentence. When carbon dioxide from the atmosphere dissolves into seawater, it alters the carbonate chemistry of the water, leading to ocean acidification. The ocean is not a bucket of water that mixes instantly, Exchange between the surface and the deep ocean is slow. Different regions react differently, and ecological impacts vary due to temperature, nutrients, and pollution. However, shells, coral skeletons, microscopic planktonic exoskeletons, and organic matter deposited on the seafloor can all record past changes in seawater chemistry. In future rock cores, the Anthropocene may appear as an unusually rapid chemical shift, like a sudden deviation from the baseline on an electrocardiogram. Ice also remembers, at least as long as it remains intact. Snow in the Greenland and Antarctic ice sheets is compressed layer by layer into ice, trapping air bubbles from the atmosphere of that time. Today, we can read clues about carbon dioxide, methane, and temperature from hundreds of thousands of years ago in ice cores, precisely because these bubbles did not immediately mix with the surrounding atmosphere. If the ice sheets retreat significantly in the future due to continued warming, many recent records will melt, be lost, or be remixed. But in the ice layers that remain preserved, the industrial era changes in gases, sulfates, lead, and certain radionuclides will form a clear chapter. The problem is that one of Earth's best archives may be dismantled by the very climate we are rewriting. The atmosphere itself has left a legacy invisible to the naked eye. The widespread use of nitrogen fertilizers has altered the nitrogen cycle from the air through the soil and rivers to the oceans. Fly ash particles from coal and oil combustion settle in lakes and peatlands, and heavy metals enter sediments via industrial emissions. Some of these are absorbed by organisms, some are transported by water, and some are remixed at the surface. Taken individually, none of these signals is necessarily unique to humans. Yet, when found together in sediments from the same time period, they resemble a group of unfamiliar actors entering the scene simultaneously, indicating that some global process had suddenly accelerated. What follows makes the story even stranger. What humans leave behind may not just be things, but a reshuffling of life itself. We have brought cattle, sheep, pigs, chickens, dogs, cats, crops, pests, weeds, and pathogens to continents they could never have reached on their own. We have altered habitats, hunting pressure, rivers, and climate, causing many species to plummet in numbers or go extinct. Even if humans were to suddenly vanish, the migrations and extinctions that have already occurred would not automatically be reversed. Ecosystems would continue to evolve, but they would have no way of knowing which historical version of the world to restore. In the fossil record of the future, the most conspicuous remains may not necessarily be human bones. Although human remains are numerous, whether they are preserved as fossils depends on burial conditions, chemical environments, erosion, and geological movements. The vast majority will not leave behind complete skeletons. Instead, animals, which are numerous, widely distributed, and closely linked to human life, are more likely to serve as statistical indicators. The bones of domestic chickens, livestock, pets, and certain urban-adapted species may form exceptionally dense records at many sites. While they may not prove human habitation at every location, they will tell future researchers that, during a brief era, the global distribution of living organisms was rearranged by a powerful force. Domestic chickens, in particular, carry a peculiar symbolism. While the bones of wild birds appear in a variety of environments, modern broiler chickens have been selected, bred, and transported globally within an extremely short time frame. They are numerous, and their morphology and growth rates differ significantly from those of their wild ancestors. In the future, if well-preserved landfill layers, farm sediments, or urban fringe deposits are discovered, clusters of chicken bones may be more common than human bones. This is not because chickens are more important than we are, but because the fossil record does not preserve importance. It preserves only abundance, probability of burial, and the durability of the material. The traces left by extinction are even more silent. The fossil record is inherently incomplete. The disappearance of many species from the strata does not necessarily mean they went extinct at that precise moment. The scale and ultimate outcome of the modern biodiversity crisis remains subject to future actions and cannot be prematurely written off as a completed geological mass extinction. However, if a large number of lineages decline or vanish within a relatively short geological time frame, future sedimentary layers will reveal abrupt shifts in community composition. Certain shells will no longer appear, pollen assemblages will change, bones of large animals will become scarce, and invasive or disturbance-tolerant species will increase. That void will be harder to explain than any monument. From this point onward, the human legacy is no longer merely what we created, but whom we enabled to exist. A collapsed bridge can turn to rubble, and a corroded coin can become oxide, but a lost species will not grow back from the rock strata thousands of years later. Evolution will, of course, continue. New species will fill ecological niches, and forests and oceans will forge new relationships. Yet evolution is not an undo button. The Earth of the future may flourish, but it will not be the same Earth that existed before we left. This also leads to different answers to the question of what will be remembered in the end. If we consider human artifacts, certain remnants buried deep in landfills, mines, tunnels, and arid regions may persist for a long time. If we consider chemical signatures, radionuclides from nuclear tests, disturbances in the carbon cycle caused by the burning of fossil fuels, industrial fly ash, and heavy metals may be more widespread. If we consider the impact on life, the fossil assemblages resulting from species extinctions, domesticated animals, and global biomigration may span a much longer evolutionary timeframe. No single trace can alone span all timescales, but when layered together, they form a stratigraphic record that is nearly impossible to misidentify. When geologists discuss the Anthropocene, they are specifically addressing whether such a stratigraphic unit can be clearly identified. The term is widely used in scientific, cultural, and public discourse, but its designation as an official geological epoch has been subject to rigorous procedures and controversy. Regardless of its official name, the crucial fact remains unchanged. Since the mid-20th century, various measurable signals have intensified dramatically on a global scale. Nuclear fallout, industrial fly ash, plastics, nitrogen changes caused by chemical fertilizers, heavy metals, greenhouse gases, concrete, and changes in biotic communities are not abstract concepts. They have already begun to appear in the sedimentary record. But geological strata are not cameras. They lose information and can also mix it up. Rivers erode old sediments, waves reshape coastlines, insects and roots churn the soil, glaciers scrape away vast swaths of the Earth's surface, and plate tectonics cause seafloor rocks to subduct into the mantle. Not every piece of plastic produced today, every block of concrete poured, or every emission released is automatically guaranteed permanent preservation. What will truly remain in the future is that tiny fraction that happens to be rapidly buried, spared from erosion, and not subjected to deep metamorphism or recycled into the Earth's interior. This may sound cruel, but it is the reality of paleontology. The dinosaurs we see today do not represent all life from the Mesozoic era, but rather survivors selected through a combination of countless fortuitous preservation conditions. Many geological periods have left behind only teeth, shells, pollen, or chemical anomalies. Many spectacular organisms and landscapes have left no recognizable traces at all. Future researchers won't have access to complete video footage of human cities either. What they might find is just a thin layer, one mixed with microplastics, metal shards, a sudden surge in soot spherules, anomalous nitrogen isotopes, plutonium isotopes, and a sudden shift in the fossil assemblage. Yet based on this single layer alone, they might still infer an extraordinary cause. Imagine a geologist living 10 million years from now, cutting open a rock core from a lake or ocean floor. She first sees normal sediments, mud, sand, shells, pollen, and volcanic ash. Then, in a very thin section, a large number of elements appear that should not coexist. Countless tiny black combustion particles, evidence of high-temperature burning, fragments of aluminum and metal alloys, evidence of large-scale smelting, traces of organic polymers, evidence of man-made materials, anomalies in radioactive isotopes, evidence of a nuclear age. And at the same time, pollen and skeletal remains would tell her that the distribution of life had been rearranged within an extremely short period of time. She wouldn't need to find a cell phone to know that some kind of planetary scale event, beyond ordinary ecological change, had occurred here. But she might not know who we are. She might guess that industrial activity once took place here. She might infer that fossil fuels and nuclear technology were used. She might even realize that some intelligent species altered the environment. Yet she might not know how many languages humans speak, how we love, argue, compose music, or tell stories, nor how an ordinary person in a city spends a day. The geological record excels at preserving energy, materials, and ecological consequences, but it does not preserve meaning. Earth may remember that we altered the air, but it will not remember why we wrote a particular poem. This is the most unsettling aspect of civilization. We have spent millennia accumulating writing, laws, mathematics, music, and memories, yet we have stored them on the most fragile of media. At the same time, the legacies most likely to survive deep time are precisely those we do not wish to leave behind. Pollution, greenhouse gases, species loss, fallout from nuclear tests, and materials that are difficult to degrade. Our most refined expressions of self are prone to vanishing, while our most brutal acts of planetary transformation are, paradoxically, harder to erase. The Earth's archives are not organized by value. They are preserved solely according to the laws of physics. But this is not the end of the story. Tens of thousands of years from now, ice ages, sea levels, and rivers will continue to reshape the Earth's surface. Slow changes in Earth's orbital parameters will affect the distribution of solar energy across different latitudes and seasons, and the climate system will continue to adjust amid natural variability and the long-term forcings left behind by humanity. Coastlines may advance or retreat, and many sites where cities stand today will undergo sedimentation, erosion, or repeated submersion. Ruins buried in stable basins will be preserved, while those exposed in mountainous regions, along coastlines, or in river valleys will be ground down into unrecognizable particles. Deep time is not a clock ticking uniformly, but a machine that constantly shifts materials. 100,000 years is almost equivalent to eternity in the human imagination, but for the Earth, it is merely a fleeting moment. Ice ages will advance and retreat, rivers will change course, deserts will migrate, and coral reefs will grow and die. Without human maintenance, many dams will eventually silt up, leak, overflow, or fail during extreme floods, the exact timing depending on their design, geology, and watershed conditions. What they leave behind are not eternal walls, but altered river valley deposits, lakebed sediments, and sudden hydrological events. Humans once believed they could control rivers, yet the Earth will rewrite that control into a sedimentological record. Millions of years from now, the vast majority of urban traces exposed at the Earth's surface will be unlikely to survive intact. Yet certain deeply buried mines, boreholes, geological disturbances, and waste repositories may still persist underground with unnatural geometries and compositions. Wellbores left by oil and gas extraction, along with alterations to underground reservoirs and traces of injection, may, if sealed by subsequent sediments, become a peculiar underground texture. Future geologists may discover that, during a very brief period, the shallow layers of the Earth's crust were perforated with numerous vertical holes, as if repeatedly pricked by the needles of a sentient being. Yet even these pinholes are not guaranteed to last forever. The crust moves slowly, groundwater circulates, faults shift, and mountain ranges rise and are eroded. The average annual movement of a continent is equivalent to the growth of a fingernail, but over 10 million years that amounts to hundreds of kilometers, and over 100 million years, it is enough to render today's familiar maps meaningless. The Atlantic Ocean will continue to widen, or, in the even more distant future, begin to reassemble. New ocean basins will form, and old seafloors will subduct. The Earth's surface is not a monument's pedestal, but a conveyor belt that is constantly recycled and remade. The oceanic crust is particularly poor at preserving ancient memories. It forms at mid-ocean ridges, moves outward on both sides, and eventually sinks into the mantle at subduction zones. The age of the existing seafloor is generally far younger than that of the oldest rocks on land, because old seafloor is constantly being recycled. Therefore, certain human signals deposited on today's deep seafloor may have a chance of surviving for millions of years, but they may not necessarily endure across the extremely long geological timescale. Locations more likely to preserve long-term records include stable, erosion-resistant continental basins, lakes, polar ice deposits, or unique cave environments. But even there, preservation is a matter of probability, not a guarantee. This brings to mind a larger counterintuitive fact. There are not many of the Earth's oldest continuous surfaces. Mountain ranges appear immortal, yet in reality they are being gradually eroded by wind, ice, water, and chemical reactions. Coastlines appear fixed, yet in reality they are constantly receding due to tides, storms, and sea level changes. Most of the streets we walk on today, the buildings we see, and the objects we collect have existed for far less time than a single grain of rock. The span of human civilization is not even a thin line between the names of geological eras. Yet the changes we've caused may be just enough to leave a sharp inflection point on that line. On a time scale of tens of millions of years, the question shifts from which objects remain to which consequences remain. Even as plastics degrade, radionuclides decay, and cities are buried, the paths of species evolution have already diverged. An extinct lineage will not automatically return. A plant or animal introduced to a new continent may continue to diversify. and a modified river system will set a new starting point for future ecosystems. Future life will fill the world, but its phylogeny and geographic distribution will bear the imprint of the human era. Earth's deepest memory may not be an object, but rather a tree of life that we have pushed toward a different fork. If human activity is ultimately identified in future geological strata as a rapid global disturbance, it may be compared side by side with past events. Ancient Earth experienced massive volcanic eruptions, meteorite impacts, oceanic anoxia, glacial transitions, and large-scale disruptions to the carbon cycle. Those events did not require civilization to leave a profound record. Future researchers will not ask, "Is this human?" but rather, what process could simultaneously alter carbon, nitrogen, metals, radioisotopes, sediments, and biotic communities within such a short geological time frame? Humanity's uniqueness will not stem from a single intact structure, but from the speed at which many different systems were driven simultaneously. But there is another often overlooked candidate for man-made traces: satellites in orbit. When humans leave Earth, low-orbit satellites are subject to drag from the thin atmosphere, causing their orbits to gradually decay until they eventually re-enter the atmosphere and burn up or crash to the ground. This process can take anywhere from several years to much longer, depending on altitude, solar activity, and the satellite's shape. Satellites in higher orbits may continue to circle the Earth for a very long time, but they are subject to the gravitational pull of the Sun and the Moon, solar radiation pressure, and orbital perturbations, and communication with them has long since been lost. They may retain their shape slightly longer than many cities, but they are not the kind of memory that Earth's rocks will preserve forever. Spacecraft in geosynchronous orbit are particularly akin to forgotten timepieces. Located approximately 36,000 kilometers above the Earth's surface, far from atmospheric drag, they may remain in Earth's vicinity for a considerable length of time. Yet, a considerable length of time is still not deep time. Orbits evolve slowly, the probability of collisions accumulates, and solar activity and gravitational perturbations also alter their positions. Even if certain fragments continue to orbit long after humanity has completely vanished, they will ultimately be nothing more than fleeting afterimages near the planet. The question is what Earth will remember, not what space will leave behind. In this regard, satellites stand less chance than a piece of plastic buried in rock or an isotopic anomaly. The Moon might preserve these remnants longer, as it lacks rain, wind, rivers, and active tectonic plates. It has no atmosphere to corrode metal, nor forests to swallow up landers. But that is the Moon's memory, not Earth's. Apollo landing sites, probe debris, and human artifacts may persist on the lunar surface for an extremely long time, though they will still be slowly eroded by micrometeorite impacts, solar wind, and temperature cycles. They offer a poignant contrast. Everything humanity creates on Earth is rapidly rewritten by the active planet, while the few items we've left on a lifeless moon may, paradoxically, outlive us. Are there any particularly durable human artifacts left on Earth? Gold, platinum, and certain ceramics are indeed resistant to corrosion, and glass may also survive for a long time when deeply buried. But they are limited in quantity, unevenly distributed, and over long periods may have been moved, melted, or trapped in hard-to-find places. The strongest evidence for future geology will not come from a single exceptionally durable ring, but rather from the most widespread combination of anomalies. Just as the iridium layers left by asteroid impacts are so compelling, not because a single grain of iridium never disappears, but because anomalies of the same type appear simultaneously at many locations around the globe. Human roads, farmlands, and cities also leave geomorphological traces. We excavate mountains and reclaim land from the sea, alter river courses, build canals, cut through hillsides, pile up mine tailings, extract groundwater, and change the way sediment flows into the ocean. Many of these changes will be partially covered by floods and vegetation over the course of decades or centuries. Yet certain large-scale engineering projects will influence sediment flow patterns for much longer. A blocked estuary, a reclaimed stretch of coastline, or a massive pit left by a mine may persist in the landscape until erosion rounds off their edges. While they will not retain the precision of architectural blueprints in the deep time, they will alter where subsequent sediments settle. Agriculture, too, is not merely a visible trace, but a process that alters the Earth's surface. Human cultivation, fertilization, irrigation, and grazing have altered soil structure, carbon storage, erosion rates, and pollen composition. After land is taken out of cultivation, some soils may reaccumulate organic matter, while in other areas, the topsoil may be lost to erosion. Field ridges and irrigation channels will be washed away, and terraced fields may collapse, but the soil and sediments that have been moved by human activity over the long term will not necessarily return to their original locations. In future sedimentary layers, there may be no sign labeled farmland, but there will be evidence of an unusually rapid period of erosion, nitrogen input, and vegetation community transition. Now let us turn our gaze deeper underground. The extraction of coal, oil, natural gas, and metal ores means that humans are reconnecting materials that were originally separated at different depths within the Earth's crust. We extract carbon and metals from the ground and release them into the air, water bodies, cities, and waste. We also inject drilling fluid, carbon dioxide, wastewater, and other substances back into the ground. Such mass transfer is not entirely unprecedented in Earth's history. Volcanoes and erosion also transport elements, but the scale and direction of human-driven transport, concentrated over an extremely short period, will alter local geochemical conditions. Even after the structures that house them are gone, future rocks may retain this artificially disrupted distribution of elements. However, any narrative about what the Earth will ultimately remember must acknowledge an uncomfortable truth. The Earth also forgets. Rocks erode into sand. Sand becomes sedimentary rock. Sedimentary rock is buried deep underground, where high temperatures and pressures cause minerals to recrystallize. In the most extreme cases, the crust subducts, carrying the original records into the mantle, where they melt and lose their original structure. The Earth is not like a hard drive. It is more like a library that constantly breaks down old books into pulp and uses that pulp to create new ones. While rocks dating back billions of years do indeed remain on the continents, they are extremely rare survivors. For a thin layer from the human era to remain intact across hundreds of millions of years, it would need to be buried in a suitable basin, shielded from mountain formation, glacial erosion, coastal erosion, metamorphism, and subsequent sedimentary disturbances. Such conditions are not impossible, but they are difficult to predict. Therefore, the most honest answer is not that any particular substance is bound to survive the longest, but rather that certain geochemical and biological traces are most likely to be discovered in the future within suitable rock layers. There is another exaggeration often used when discussing the future: the claim that plastic will last forever, or that radioactive waste will make the Earth glow forever. Both statements highlight the long-term nature of these issues, yet neither is entirely accurate. Plastics will be altered by light, oxidation, wear, and chemical processes. Radionuclides will decay, and waste will be affected by containment and geological conditions. Long-term does not equate to infinite. What is truly sobering is that the timescale of this legacy far exceeds political cycles, corporate lifespans, and human memory. It does not need to last forever. Spanning thousands to hundreds of thousands of years is sufficient to make us rethink the extent of our responsibility. Similarly, ecological recovery after human extinction cannot be portrayed as a self-sustaining pastoral idyll. Without human pressure, some habitats may recover, and some predators and large animals may expand their ranges. Yet climate change, invasive species, pollution, and extinctions will continue to shape the outcome. Certain animals bred by humans may thrive in the short term, while others will rapidly decline due to the loss of human care. Areas of nuclear contamination, extreme drought, heavy urbanization, and watersheds altered by dams will not all follow the same script. Nature will take over, but it will inherit the reality we leave behind, not an untouched Eden. If there are no new sentient observers in the future, whether Earth remembers us seems to have become a philosophical question. Isotopic anomalies in rock layers will not be read by any eye. Plastic debris will not be picked up by any hand, and deviations in species evolution will not be named. Yet physical facts do not require an observer to exist. Traces of the age of the dinosaurs existed long before we appeared. Similarly, traces of the human era will continue to influence sedimentation, chemistry, and life as part of the material world, even if no successors ever discover them. The Earth's memory does not exist to be read. It is simply the consequence of change. And if a new intelligent species were to emerge in the future, or if a distant civilization were to arrive here, they would be faced with a peculiar archaeological mystery. They would not first discover our language, nor would they first discover the Internet. It is more likely that they would first observe anomalies in rocks and sediments, and only then search for local remains. They might infer the rapid release of ancient carbon from global carbon isotope shifts, deduce nuclear technology from nuclide layers, identify synthetic polymers from material fragments, and conclude that the planet was massively altered based on mutations in biological communities. Whether humanity is accurately identified will depend on how much evidence has been preserved, as well as on the capabilities of their scientific tools and concepts. This is not so different from our own situation when studying the distant past. We infer asteroid impacts from a thin layer of clay, ancient ocean anoxia from microscopic fossils and isotopes, and long-vanished organisms from teeth, pollen, and footprints. We do not need to hear the sounds of the past to know what once happened. Future geologists may view us in the same way, not as countless individual beings, but as a process that left measurable traces on a planetary scale. But the real mystery lies even further ahead. If humanity were not to vanish tomorrow, but were to continue existing for thousands or tens of thousands of years, the memory we leave behind would be entirely different. If we continue to burn fossil fuels, the chemical and biological signals will be stronger. If we restore ecosystems, control emissions, and reduce pollution, the spikes in future rock layers may be shorter and weaker. If we send more material into space, the legacies on Earth and the Moon will diverge. The question may seem to be about the traces we leave behind after we die, but it is actually about the choices we make while we are alive. Earth has not yet sealed this layer. We are still determining its thickness and composition. Therefore, Anthropocene is not a term reserved solely for geologists. It reminds us that human activity is no longer merely a local event confined to a single country, river, or city. We are moving carbon, nitrogen, water, rock, and living organisms on the scale of the Earth system. The most terrifying aspect of this scale is that it has no clear boundaries. The exhaust from a single car, a piece of plastic packaging, a dam, or a cleared patch of forest, each is small on its own. Yet when billions of such small actions are stacked together, they become a global signal embedded in the rocks of the future. Looking back from a 1,000-year perspective, human traces may still appear vast. Many building foundations remain. The outlines of dams and canals and valleys are still clear. Cemeteries, roads, metal artifacts, and deeply buried fragments of cities can still be unearthed. If the climate is dry, earthquakes are rare, and sediments happen to cover them. Certain inscriptions may even be preserved. But 1,000 years is not the time scale at which the earth truly begins to speak. To the rocks, 1,000 years is more like a fresh footprint. They have not yet decided whether this footprint will be dried out, washed away, or buried under the next layer of silt. 10,000 years from now, the loss of language will be more complete than the collapse of buildings. Language itself depends on successive generations to pass it down, while writing relies on materials and traditions of interpretation. Without users, even the hardest inscriptions will gradually become mere patterns. If some future intelligence discovers them, it may be able to infer from recurring structures that they are symbols, but it may not be able to restore their precise meanings. This is already the case today when we encounter many ancient scripts. Seeing the engraved marks does not mean we can hear the speaker's voice. What humanity has left behind most abundantly is not readable stories, but a silence that cannot be automatically translated. 100,000 years from now, the cities that remain will resemble anomalous landforms rather than centers of civilization. Subway stations will be filled with sediment. The corrosion of steel reinforcements in buildings will leave mineral stains, and shards of glass and bricks will become part of the soil layers. Sea levels, rivers, and glaciers will determine which areas are buried and which are eroded. If someone in the future were to excavate along a cross-section, they might see regular concrete blocks, metal oxides, and unusual cavities, yet it would be difficult to reconstruct, based on these alone, the speed, noise, love, wealth, poverty, and dreams that once characterized a city. 1,000,000 years later, most local remains will have lost their distinct boundaries, but global signals will begin to take precedence. Fly ash, radionuclides, plastic residues, and isotopic variations buried in stable sedimentary basins may still form a comparable window into the past. At this point, the most compelling clue is not that a building is still standing, but rather the appearance of the same type of anomaly at many distant locations. This is precisely how geological eras are defined, not by a single legendary site, but by common markers that can be identified across different rock strata. 10 million years from now, the chances of preservation will be drastically reduced. Many surface records will have long since been eroded, and much of the seafloor record will have migrated toward subduction zones. But certain lacustrine, deltaic, or oceanic basin deposits within continents may have already solidified into rock. They will compress the human era into a segment perhaps only a few centimeters thick, or even thinner. To future researchers, this will resemble our current encounter with the late Cretaceous boundary, an astonishingly thin layer of material that nonetheless represents a global-scale catastrophe and reorganization. The human material era may be much the same, brief yet extremely dense, 100 million years from now, the world map will be unrecognizable. Mountain ranges will have been eroded, new ranges will have risen along collision zones, and today's ocean boundaries will no longer exist. No matter how clear the preserved human signals may be, they will be folded, fractured, altered, or buried deeper within the Earth's crust. Only a tiny handful of fortunate rock layers will make it through this span of time, bearing still recognizable patterns, much like old letters salvaged from the deep sea. By then, words like plastic, nuclear tests, and cities will have long since lost their meaning. All that remains will be anomalous polymer residues, isotopic ratios, mineral assemblages, and biological succession. Therefore, what the Earth can remember is never the complete human being. It cannot remember a child's name, nor how a melody brings tears to one's eyes, nor how we stayed up late writing a letter. What it can preserve are the shadows of our impact on the material world. A deviation in the carbon cycle, a layer of enriched metals, a batch of suddenly appearing synthetic particles, a river that has been diverted, or branches that have vanished from the tree of life. The human inner world is so complex, yet what ultimately gets imprinted on the rocks may be only a tiny fraction of measurable external consequences. Here lies a reversal worth pausing to consider. We often build monuments soaring high, hoping they will tell future generations of our former greatness. Yet what is truly more likely to span deep time is not what rises toward the sky, but what sinks deep into the Earth's strata. Not the spires of palaces, but the debris in landfills. Not the most beautiful libraries, but the carbon left after fuel burns. Not the most sophisticated computers, but the layer of isotopes that settles into the soil after a nuclear test. The aesthetics of geological time are the exact opposite of those of humanity. It favors burial, repetition, and vast scale over glory. This is not to say that all of humanity's beautiful creations will vanish completely. Certain works of art, stone carvings, ceramics, architecture, and texts may endure for a very long time due to fortuitous preservation conditions. Perhaps future archaeologists will discover a sealed space, decipher a small portion of a language, and piece together a face or a musical passage. But these will be exceptions. Lucky fragments preserved by deep time from among countless losses. We cannot pin our hopes on exceptions, nor can we mistake fleeting legibility for permanent existence. If we compare the Earth to an extremely slow camera, the exposure time of human civilization is very short, but the light is extremely intense. Early agriculture, cities, empires, and the Industrial Revolution may blend together in the rocks of the future as a gradually intensifying prelude. The Great Acceleration since the mid-20th century, however, resembles a suddenly triggered flash. Energy consumption, population, material production, fertilizer use, transportation, plastics, and nuclear technology all expanded simultaneously over a very short period. Future geological strata may not be able to distinguish every country or every invention, but they may reveal how the overall brightness suddenly surged. The deepest risk is that we still treat this exposure as a draft that can be undone at any time. Many environmental changes can indeed be mitigated, certain forms of pollution can be remediated, ecosystems can recover under protection, and reduced emissions can prevent further cumulative harm. But the Earth system will not instantly reset everything that has already happened. The heat absorbed by the oceans, the adjustments to ice sheets, the species that have gone extinct, the materials that have been dispersed, and the geological strata that have been formed will all continue to evolve. We are not powerless. We simply do not possess the magic to turn back the clock. This is why the notion of human extinction should not be portrayed as a romantic escape. It does not automatically give the Earth a clean slate. Even without a single human being, greenhouse gases would still circulate within the system. The oceans would continue to respond due to past heat absorption and chemical changes. Certain pollutants would still move through food webs and sediments, and the ecological lineages that have been severed would remain absent. Nature is not a cleanup crew. It is a complex system that will continue to evolve under existing conditions. The world we leave behind will become the starting line for future life. Looking further ahead, the existence of the Sun will pull all Earth-scale problems back to the cosmic scale. The Sun is not a constant light bulb. It is now approximately 4.6 billion years old and remains in the main sequence phase, steadily burning hydrogen, but it will slowly brighten as it evolves internally. This change is nearly imperceptible over the span of a human civilization, yet on a timescale of hundreds of millions to billions of years, it will become a decisive factor. The fact that Earth is suitable for liquid water today does not mean it will always be so. Scientific models still differ on the details of the distant future, as clouds, the carbon cycle, plate tectonics, and atmospheric escape all interact with one another. But the general direction is clear. As the Sun gradually brightens, Earth's window for sustaining complex life and oceans will eventually close. This is not a disaster that can be averted by patching up dams, but rather a long-term boundary imposed by the Sun's life cycle. By then, the layers of plastic, concrete, isotopes, and fossils left behind by humanity, even if they remain embedded in certain rocks, will face an increasingly hot and alien planetary environment. In about 5 billion years, the Sun will emerge from its current stable phase and expand into a red giant. The fates of Mercury and Venus are all but sealed, while whether Earth will be directly engulfed by the expanding Sun still depends on details such as the Sun's mass loss, tidal forces, and orbital evolution. Different models have uncertainties regarding the final stages, but no model allows for the Earth's surface to remain intact as it is today. Even if Earth temporarily avoids being swallowed, it will be baked by intense radiation. The oceans will have long since evaporated, and the rocks and atmosphere will be completely reshaped. On that scale, all cities, rock cores, monuments, and technological fossils would amount to nothing more than an extremely thin layer. If Earth were swallowed by the expanded Sun, the entire geological record would end within the star. Even if Earth were to migrate outward after the Sun loses mass and briefly escape being swallowed, it would still face a surface that is nearly unrecognizable. Human artifacts will not endure like museum exhibits until the end of the universe. They belong to a living planet, and a living planet will ultimately be rewritten by its star. This leads to a more sobering conclusion. From a cosmic perspective, Earth will ultimately remember nothing of humanity. Ultimately, the Sun, collisions, melting, and the long geological cycle will rewrite every layer of the record. The concept of last can only hold true within a finite window of time. If the question is what is most likely to be preserved long-term in Earth's rock layers after humanity disappears, the answer is a composite signal. If the question is what will still exist right up until Earth's destruction, there is no single definitive candidate. Perhaps nothing will remain intact. But finite does not mean insignificant. The age of the dinosaurs ended 66 million years ago, yet we can still learn from a single layer of rock how their world was transformed by a sudden impact. The ancient oceans have long since evaporated and reformed countless times. Yet we can still discern one of their anoxic events from isotopes and microfossils. A record need not be eternal to be meaningful. It merely needs to serve, over a sufficiently long period, as evidence for later generations to understand cause and effect. The geological strata left behind by humanity may be no different. They need not survive until the end of the universe to tell the story, millions of years from now, of how a powerful species transformed its own planet. So, the final answer can be stated with greater precision. What will disappear last is unlikely to be a building, a set of data, or a work of art. It is more likely to be the composite fingerprint left behind after humanity pushed the Earth system off its original course, the isotopic shift in ancient carbon from combustion, artificial radionuclides from nuclear tests, industrial fly ash and metals, anomalous fragments of plastic and concrete, globally transported species, and gaps in biodiversity left in certain places. These are not a name, but a narrative that cannot be easily forged. And among these candidates, what comes closest to what the Earth will ultimately remember may not be any material at all, but rather the changes to life itself. Plastic will degrade, radionuclides will decay, and rock layers will be recycled. But an extinct lineage, a redistributed ecosystem, or an evolutionary branch that has diverged due to changes in climate and land, these can leave a lasting impact. Future species will not remember humanity, yet they may live within the genetic and geographical conditions we have altered. That memory has no words, yet it is inscribed in the bodies of every descendant. This is not meant to instill despair. On the contrary, it makes the present clearer. We are not observers standing outside Earth's history. We are already a layer of sediment in the process of formation. Every generation adds material, energy, and choices to this layer. Future rocks will not judge us as good or evil, but they will faithfully record the direction we took. Whether we allow this layer to become a fleeting and reversible disturbance, or a long and barren dividing line, still depends on what we do while the record remains unsealed. Perhaps one day no one will speak of humankind anymore. No one will understand our language, and no one will find a complete face among the ruins. Yet at the bottom of some lake, in some bay, within some ice core, or in some layer of future rock, there will still be an extremely thin boundary. On one side of that boundary lies a world without plastic, without nuclear fallout, and without such a rapid carbon transition. On the other lies a planet suddenly transformed by a short-lived yet powerful species. That is how Earth may remember us. We are not Earth's masters, nor will we ever be its permanent masters. We are merely a form of life that emerged very late in its 4.6 billion year history, yet we possess the power to alter the atmosphere, the oceans, the rocks, and the web of life. The universe will not preserve our records, nor will Earth forgive our mistakes. But during this brief window, while the planet remains warm, while the oceans persist, and while life capable of interpreting the evidence still exists, we can decide. Will future rock layers reveal a silence born of destruction, or a civilization that finally learned to coexist with the world upon which it depends? It is worth asking once more, why might landfills be more likely than museums to enter deep time? The answer lies not in the fact that trash is more durable than art, but in burial. Sunlight, oxygen, and water are the enemies of many materials. Once objects are rapidly buried in low oxygen, relatively stable sediments, certain decomposition processes slow down significantly. Landfills concentrate staggering quantities of paper, plastic, textiles, metal, glass, and food scraps in one place, and are often covered by layers of soil. They will not become eternal time capsules. Leachate, microorganisms, compaction, and groundwater will continually alter their contents. Yet from the perspective of stratigraphic preservation, these places, unvalued by humans, may actually have a better chance than display cases of leaving behind a chaotic yet rich material archive. This does not mean that the 21st century can be fully reconstructed from landfills in the future. Burial crushes structures and chemical reactions alter materials. Even if future generations discover a layer of waste, they may see only unclassifiable debris. Yet they can offer the power of co-occurrence, the simultaneous presence of glass, ceramics, plastic, aluminum foil, electronic materials, pharmaceutical residues, and organic matter comes far closer to outlining a technological society than a single gold coin or a fragment of bone. For future geologists, what matters most may not be the identity of any single object, but rather how unusual this combination of materials is within its natural context. The seafloor also receives legacies from land. Rivers carry particles eroded from cities, residues from industrial emissions, soil washed away from farmland, and plastic debris to estuaries. Ocean currents then transport a portion of these materials to the continental shelf, the abyssal plain, and oceanic trenches. Sedimentation rates vary from place to place. In some areas, the record is disturbed by marine life or dispersed by ocean currents, while in others it accumulates in relatively stable layers. The deep sea is not a giant bottomless trash can, but rather a slow, complex transport system. It disperses human-derived materials over a wide area, while also turning a few locations into exceptionally clear repositories. Biological disturbance is a challenge future interpreters must confront. Worms, shellfish, and other benthic organisms burrow, feed, and transport particles within seafloor sediments, mixing what were once distinct annual layers into a broader, thicker range. Floods, storms, and landslides can also displace years' worth of sediment in a single event. As a result, a signal from a specific era may not appear as a razor-sharp line, but rather as a churned-up banded zone. This does not erase human traces, but it does require future researchers to cross-validate their findings using multiple locations and multiple indicators. True science never treats a single rock as the sole piece of evidence. Black carbon particles left behind by air pollution serve a similar purpose. The high-temperature combustion of coal and oil produces tiny carbon-rich spherical or irregular particles that can be carried by the wind to lakes, glaciers, and oceans far from cities. Volcanoes and wildfires can also produce combustion byproducts, so a single black carbon particle cannot prove the existence of the industrial age. However, when fly ash morphology, heavy metals, fossil fuel, carbon isotopes, and other industrial signatures appear together, they point the same story in a clearer direction. During a certain period, combustion ceased to be merely localized flames and became a planetary-scale energy system. The Anthropocene layers in future rock strata may also exhibit striking geometric features. Natural sedimentation typically follows topography, river courses, wind patterns, and biological activity. Humans, however, tend to create straight boundaries, regular cross-sections, pits of uniform depth, long stretches of parallel roadbeds, and unusually thick fill deposits. Even if these geometric features are eventually eroded beyond recognition, certain cross-sections may still reveal abruptly truncated soil layers, infilled heterogeneous materials, and deposits with unnatural slopes. While these do not automatically prove intelligence, They will lead researchers to suspect that a force once existed that did not merely follow the terrain, but sought to reshape it into a tool for its own purposes. Dams and large reservoirs provide a particularly clear example. Dam construction alters upstream sediment deposition, downstream nutrient levels, and riverbed erosion, and temporarily traps materials that would otherwise be periodically transported to the coast. Dams that are no longer maintained may fail at different times and in different ways. But whether through long-term silting or sudden breaching, they leave behind unnatural sedimentary sequences in the river valley. Future geologists may never know the names of those who built the dams, but they may observe that a stretch of river was once artificially paused, only to be restarted by an exceptional flood. What about urban heat islands, nighttime lights, and radio signals? They are extremely conspicuous today, yet they have almost no durability over deep time. Unmaintained lights will go out when the power grid fails, radio transmissions will fall silent when equipment breaks down, and localized urban warming will fade as buildings are demolished, vegetation returns, and the global climate continues to change. This reminds us not to mistake what is most easily visible from satellites today for what the Earth is best at preserving. Visibility and preservability are almost opposite physical properties. The Earth can also preserve humanity's chemical signature. Industry has synthesized many compounds that rarely occur in the natural environment or exist in different forms there. Some of these will degrade, while others may leave stable residues or transformation products in sediments. Whether they can persist for hundreds of thousands of years depends on molecular structure and the environment. There is no one-size-fits-all answer, but together with plastics, metals, and radionuclides, they will make future geological strata appear unlike the result of a single natural process. The reason human traces are so difficult to erase completely is not because any single material is indestructible, but because we have altered so many material cycles simultaneously. Perhaps future researchers will make mistakes, misinterpreting certain natural anomalies as human in origin, or mistaking human traces for volcanic impact or climatic events. This is entirely possible. The history of science is, by its very nature, a process of continually correcting misinterpretations. Precisely for this reason, reliable conclusions require independent lines of evidence to support one another. Whether the dating is consistent, whether the distribution is widespread, whether the materials required high-energy production, and whether biological and chemical changes can be explained by the same mechanism. The reason we can be certain today that the extinction of the dinosaurs was linked to an impact is not based solely on a single iridium sample, but rather on a network of evidence comprising impact craters, shock quartz, global boundary layers, and patterns of mass extinction. If humanity is ever identified in the future, it will be in the same way. No single piece of evidence bears the entire burden of proof. Plutonium isotopes mark the nuclear age. Plastics indicate synthetic materials. Fly ash and carbon isotopes indicate combustion. Concrete and metals indicate manufacturing. Species distributions indicate ecological dispersal. And ice cores and marine sediments indicate changes in atmospheric chemistry. They are like multiple arrows all pointing in the same direction. Even if one of them breaks during weathering, the other arrows may still provide sufficient direction. This also illustrates that humanity's deep time legacy does not amount to complete proof that humans once existed. A future civilization might be able to determine that Earth once underwent an extremely unusual period of industrial disruption. But inferring from rocks that the species responsible for that disruption possessed language, ethics, family, art, and self-awareness, is a much bolder leap. The geological record can tell them how energy was used, but it may not necessarily tell them how those who used it understood themselves. The same is true when we encounter ancient life. Bones and tools can provide clues, but they cannot fully reconstruct the inner world of a vanished civilization. From this perspective, the most precious legacy may not lie on Earth at all. If knowledge can be continuously passed down, through education, documentation, culture, and future generations, it need not wait for rocks to prove its worth. Yet this very continuity of knowledge depends precisely on living societies. Without readers, a library is merely paper. Without interpreters, a formula is merely a symbol. Without maintainers, a machine is merely material. A civilization's true memory has never been the storage medium itself, but rather each generation's willingness to rekindle its meaning. Thus, the sadness of this title lies not in whether humanity leaves behind trash, but in the fact that humanity's disappearance means the interpreters have vanished as well. The Earth will still bear the consequences, but no one will be left to explain what those consequences are. We are able to decipher the Earth's past scars today because there are still living beings asking questions, building instruments, and comparing evidence. If this ability were to vanish from the Earth, rock layers would continue to settle, the oceans would continue to churn, and the sun would continue to illuminate an unread archive. And it is precisely here that the scale of deep time actually brings the present closer. 5 billion years sounds unimaginably distant, and 100,000 years sounds inconceivable. But the next emission, the next habitat to be protected or destroyed, and the next structure to be built or demolished, all of these are adding measurable content to the rock layers of the future. We are not waiting for some distant future to judge us. Rather, every day we are actively creating the evidence that future generations will read. Geological time moves slowly, yet the formation of the record is happening right now. Ultimately, there is no single word suitable for engraving on a monument to describe what the Earth will remember last. It will not be a pyramid, nor a piece of plastic, nor merely nuclear waste. The best scientific answer is a set of traces spanning multiple timescales. In the short term, cities ceasing to function and nature taking over. In the medium term, buildings turning into sediment and data becoming unreadable. In the long term, a composite stratigraphic signal composed of carbon, Euclides, materials, and biotic communities. And in the even longer term, the rewriting of all these records by tectonic plates and the sun. And perhaps the thing that comes closest to a human name is, in fact, a boundary. It does not say who we are, but it does reveal that there once was a species that released ancient sunlight from beneath the earth back into the sky, pushed the chemistry of the oceans and continents into new states, carried life from one continent to another, and, in a very short time, created materials that had never existed before. This boundary requires no language. It will lie quietly within the rock, waiting for some future eye, or perhaps never to be read at all. This planet will eventually forget us, just as it has already forgotten the vast majority of life that once existed. But forgetting takes an extremely long time, and the consequences will not wait that long. We are still within Earth's legible realm, still able to see how the air, the oceans, and life respond to our choices. The real question has never been, will Earth remember us? But rather, while we are still here and still able to understand Earth's memory, what are we willing to let it remember?